Alright, here's 2018 number 4. Real simple intermolecular force question and an ideal gas law question. National average was 1.9 out of 4. 1.9 still not good enough. We got to be able to beat 1.9. My students did this particular year. They beat 1.9, but we got it, man. We got to find points here. Not too terribly difficult. You've got two compounds. CS2, COS, they give you boiling points. Boiling points scream intermolecular forces, right? Stronger the intermolecular forces, the higher the boiling point. This is another one, they did this a couple years ago, a couple years before this, sorry, where this guy has stronger intermolecular forces, but all he has is dispersion force. That's a non-polar molecule. This COS here in this is a polar molecule, so it has dispersion forces and dipole forces. But the combination of those two is weaker than just the dispersion forces. I hate that question. I like the question fine if the polar thing has the higher boiling point, but just they're not trying to trick you. Maybe they are trying to trick you, I don't know. But use the boiling points and understand this has to have the stronger intermolecular forces. The funny part is they asked it again in 2019. Very similar question. Like that. So the combination of these intermolecular forces is weaker than the IMS and CS2. That happens to be part A in this thing. So number 4 says, in terms of types of relative strengths of all the intermolecular forces, explain why the boiling point is higher than that of the other one. Look at, you need types of intermolecular forces and strengths of those intermolecular forces in each compound. So you have to answer those things. And so here we go. Number 4A, CS2 only has only dispersion forces. The COS has both dispersion, and you can call them London dispersion if you want, forces and dipole forces. So there's the first point, is to talk about those two intermolecular forces. The intermolecular force for those two things. So just dispersion here. This guy has, everything has dispersion force because there's electrons moving around everything. This guy also is unevenly distributed, the types of atoms around the center atom. So it's dipole also. The next says, explain why boiling point of CS2 is higher than COS. CS2 has a higher boiling point because its dispersion forces are stronger than COS's combined dispersion and dipole forces. That's it. I think you could probably figure out how to write that all in one sentence. College Board point for identifying the types of intermolecular forces in both, and then the word-for-word answer for the second point is London dispersion forces in CS2 are stronger than the combination of London dispersion forces and dipole forces in COS. That's it. So that's A. There's 2 points in A, and then we come back in B. Let me squeeze it in here. B says a 10-gram sample of CS2 is put in an evacuated 5-liter rigid container. The container is sealed and heated. At which temperature CS2 all has vaporized? What's the pressure in the container once it's vaporized? Listen, volume, temperature, pressure, If you don't start with PV equals nRT with ideal gas law formula, then you are a fool, right? So that's where we're starting. We have CS2. We know this is going to be PV equals nRT, or at least we're hoping it's going to be PV equals nRT, where we are solving for pressure. They give us a volume, 5.0 liters. If you're a sig fig stickler, that guy has 2 sig figs. Then we're trying to find the pressure of the CS2. Yes, and so if we're trying to find the pressure of the CS2, we have to know the moles of the CS2. They don't give us moles of it, they give us grams of it. So we got to take those 10 grams of CS2, and we are going to turn those grams into moles for PV equals nRT. These CS2 grams are roughly 76 grams to 1 mole, and so that gives us 0.131 moles of the CS2. You actually get a point for that 0.131. I encourage you, anytime you have to plug something in a calculator, stick that in a box. So 0.131 moles, that's your first point. It's 3 sig figs because that 10 grams is 3 sig figs. And so that goes into our N value, 0.131 moles times the R value. I tell you guys, always work PV equals nRT in atmospheres. So that means that this is the 0.0821 liters times atmospheres over moles times Kelvin times our Kelvin temperature, which they gave us is 325. And so this gets multiplied by 325 Kelvin. That is a softball ideal gas law problem. If you can come up with the moles of CS2, a grams to moles, like chapter 3 of first year chemistry, and you can do a simple PV equals nRT problem, then you already beat the national average just on the second piece of this. Yes, why do people score low? Because by question number 4 in the real test, you've already done an hour and a half of multiple choice, and you're an hour into FRQs, and you're getting exhausted at this point. And so we shouldn't have that mental fatigue this year. So they didn't even make us convert anything. Be careful of units, right? Make sure if this is milliliters, it's got to be in liters. That's why I wrote this unit here. If this has got to be in moles, that's got to be in Kelvin, right? Be careful. They may say put the pressure into kilopascals or millimeters of mercury. You're capable of doing that. But that's it. We plug that guy in. The pressure. This is the least number of sig figs. Is the 2 from the liters, and so our pressure equals 0.70 atmospheres. You have to put a unit on it. And that's it in question number 4.